Good morning, students. Today we are going to see the final derivations of fifth module. Conventional force from the free end. We have already seen the stiffness matrix of the free end with conduction and conventional force at the free end. So here we know that force at free end equation is equal to H T infinity A 01. We know that H is heat transfer coefficient and T infinity is temperature of the atmosphere or temperature of the fluid. A is the area and 01. And we have already seen the equation force vector F equal to K stiffness matrix into temperature matrix. This is similar to our previous equation, force matrix equal to stiffness matrix into displacement matrix, and we are applying the values. F is FHN, which is equal to K. The K is Kc plus Kh. We have seen this in the previous problem, previous derivation, and T. And we are substituting Kc, AK by L, 1 minus 1 minus 1 1, KH, HA 0 0 0 1 0 1. And this K is thermal conductivity. And so we got the equation. And this is another main derivation. Finite element equation for one-dimensional element with conduction, convection and internal heat generation. So we have a bar with two nodes 1 and 2, and both of these ends are sealed. So the convection won't occur through this area but through both of this area, and heat is generated throughout this bar. So we have conduction, convection and internal heat generation. We know that the conduction's thermal stiffness matrix is equal to AK by L 1 minus 1 minus 1 1. Since there is no changes in the heat conduction which is flowing inside this bar, the equation for conduction is same. But in case of convection, stiffness matrix for convection, we know the equation as integral 0 to L H n transpose n ds. This ds means surface area, lateral surface area. Since the heat is generating through moving the atmosphere to both of these sides, we want to consider the lateral surface area. So we are making it as ds, and we are changing the equation as 0 to L H n transpose n perimeter P into dx. Dx we know the thickness. So we will get the lateral surface area. We are converting lateral surface area as P into dx. Now what we are going is, we are going to substitute the values of n transpose and n. We know that n for one dimension is 1 minus x by L and x by L. So while n transpose comes, it will come as 1 minus x by L and 1 minus x by L h p dx. And we are multiplying it, so we will get it as 1 minus x by L all square, x by L minus x by L square, x by L minus x by L square, x by L square. And we know that we are elaborating 1 minus x by L square, which we will get it as 1 plus x square by L square minus 2x by L. And we know that h and p are constant term. So we are taking it as outside and we are integrating this entire term. While integrating a common term, we will get it as x. And while integrating x square by L square, we will get it as x cube by 3L square. And 2x by L will become 2x square by 2L. X by L will become x square by 2L, and it will goes on. And after that, we are applying the value of L and 0, and we will get it as L plus L cube by 3L square minus 2L square by 2L, L square by 2L minus 3L cube by 3L square, and it goes on. And while while going through this things, we can see that L cube is in here, L square is in here. So we can cut it and we will get only L by 3 in here. Similarly, L square is in here, L is here. So while going through, and 2 is here, 2 is here, we will get L in here and goes on. And we will get it as HP L plus L by 3 minus L L by 2 minus L by 3, L by 2 minus L by 3 and L by 3. And while again simplifying, we will get it as L by 3, L by 6, L by 6, L by 3. We are taking L by 6 to outside. So we will get the equation as KH equal to HPL by 6 2112. And we know that the stiffness matrix K equal to stiffness matrix for conduction plus stiffness matrix for convection, that is the addition of this one and this one. AK by L 1 minus 1 minus 1 1 plus HPL by 6 2112. So we got that section, and we are going to force matrix for heat generation, which is equal to force FQ, that is Q means heat generation. FQ equal to integral 0 to L N transpose Q dV. And we already know what N transpose is and what the values of N is. That is 1 minus X by L, X by L. And we know that volume dV equal to area into thickness. So we are converting the equation as A into dx. And here Q and A is constant, and that is we are taking outside, that is we are only integrating 1 minus X by L and X by L. So we will, after the integration and substitution of L, we will get it as QA L by 2 L by 2. And while taking the common term outside, we will get it as QAL by 2 1 1. And force matrix for convection. We know that force matrix for convection equal to 0 to L H T infinity N transpose ds. So we want to substitute the value of ds as P into dx, and we are taking the common terms, that is constant terms H T infinity P outside. So we will get N transpose ds similar to here. Here also we will get N transpose ds, and I am skipping the terms, so it will get it as H T infinity PL by 2 1 1. Now we want to find out the force matrix. Force matrix F equal to FQ, that is force matrix for heat generation plus force matrix of convection plus force matrix of conduction. And we are removing the force matrix of conduction because it is very small value. That is why we are neglecting force matrix for conduction. And we know that FQ equal to QAL by 211 and FH equal to HT infinity PL by 211, and we are writing it as QAL plus PHT infinity by L by 211. And we know that F equal to KT. We already find out what F is, and we already know what K is. Here what K is, KC plus KH, and we know what T is. So while writing, we will get it as QAL plus HPT infinity L by 2 1 1. This is what K is. K, that is the stiffness matrix due to conduction, and this is what KH, stiffness matrix due to convection, that is the entire K is in here and T is here. This is the final derivation. Thank you. If you have any doubts, contact me via WhatsApp.